Okay, let's go ahead and get started. So I have up here the final problem set for the course, which is due next Monday. Just for my information, how many people have found last week's problem set, the programming exercise, reasonably doable? Well, I mean, I didn't intend it to be particularly difficult, and I do encourage you, if you're not a programming guru, to take a look at what I guess it's already due, so I don't encourage anyone to do things late, but I hope that those of you who are not programming gurus found the code that I posted online helpful. Okay, so this will be the last problem set, which is due April 5th. Just for my information, in your other classes, do you have problem sets that are due the following week? Do you know, April 12th? Something like that? Am I allowed to assign problem sets that are due the last week? Because there's that last few days of classes before exam starts. I don't think people, so I'm not supposed to assign problem sets that are due that day. Okay, good. So what that means is that, unfortunately, I won't be able to assign a problem set on gravity waves, which will be what we're covering next week. That's okay. I'm not sure. Yeah, no, there's some good problems. Well, maybe one of them will appear on your exam. Okay. Is there a class on next Monday? Or no, but this was a Tuesday, Thursday class, so...
No, I know.
Even if...
handing in the assignments for people that are not going to be on campus.
Oh, yeah, right. I guess next Monday's a holiday. So, yeah, you can turn it in on Tuesday if you're going to be out of town for the holidays or something like that. That's fine. Yeah. Right. I guess, is Friday and Monday are holidays? Is that right?
So,
okay. Good. So, let's go ahead and do some physics. So last class, I began by saying just a few words about one of the most important applications of the theory of general relativity, which is to the universe as a whole. Now, that's not to say that the other applications of general relativity are not important, but, for example, when considering solar system physics, the corrections that are due to GR are really quite small. Whereas when one is considering cosmology, especially the cosmology of the early universe, the corrections due to general relativity are quite big. I mean, there is a Newtonian theory of cosmology, and if you take an undergraduate cosmology class, then very often you will learn this Newtonian theory of cosmology. But this Newtonian theory of cosmology is only correct up to factors of order 1. And so in order to get everything correct, you really need to use the theory of general relativity. By the way, is there an undergraduate cosmology class? Is there a 500 level cosmology class? There's a 600 level one, I know. There are astrophysics classes, but there's probably no cosmology class. Okay, well that's okay, because you're going to learn cosmology now. So at the end of last class, we began with a discussion of the Copernican Principle, which is the principle that the laws of physics are the same everywhere in the universe. Now, of course, just because the laws of physics are the same everywhere, that does not mean that the state of matter or the configuration of the universe is the same everywhere. Indeed, parts of the universe have lots of matter in them, and parts of the universe do not. But what we are interested in doing is looking at the universe on very large scales, where we can approximate the matter and energy density of the universe as being roughly constant. And then what we would like to do is come up with a model for the evolution of the universe, which treats every point in space-time democratically. And so what could it mean for the universe, for the configuration of the universe to be the same everywhere? Well, there are two possibilities. One could be that space-time is homogeneous, which is the statement that for any 2 points in space-time, there is an isometry which connects them. So there's an isometry which connects any 2 points. So the statement that the universe is homogeneous is the statement, roughly speaking, that no point is different from any other point. And the other possible statement that could be meant by the statement that the universe is the same everywhere would be the statement that the universe is isotropic, which is not the statement that every 2 points look the same, but rather that there is no preferred direction in the universe. So more precisely, that would be the statement that there would be an isometry connecting any 2 vectors at each point. And so these are 2 slightly different notions of what it could mean for the universe to be symmetric. And so I think it's a useful exercise that I encourage you all to do to try and come up with examples of geometries or examples of metrics which have these different properties. So, for example, you should try to yourselves think of an example of a metric which is homogeneous but not isotropic. So that would be a space where every point is just like every other point, but yet there is a preferred direction. Or likewise, you could try and come up with a universe which is isotropic but not homogeneous. So that would be a universe where there is no preferred direction, but nevertheless there is no isometry connecting any 2 points. And so that's a useful exercise and something that I encourage you to do. And indeed, it's not so hard to come up with examples of universes which have one of these types of symmetry, but not the other. So what would it mean, however, for a universe to be both homogeneous and isotropic? Well, geometries which are both homogeneous and isotropic are very symmetric, obviously. So we know of one example of a universe which is homogeneous and isotropic, which is Minkowski space. So, as you know, there is an isometry of Minkowski space, which takes every point in Minkowski space to every other point. And these are the translations, of which there are 4. So for every point in Minkowski space, I can just do a translation, which is generated by a Killing vector, that takes 1 point to any other point. And in addition, I have Lorentz transformations. So if I start with a vector at a given point in space-time, then I could do some combination of boosts and rotations to bring that to point in any other direction. So any 2 vectors at a point in space-time are related by an isometry, namely by a Lorentz transformation, which will imply that the space-time is isotropic. And so you can see that homogeneity is associated with 4 isometries. Isotropy is associated with 6 isometries, 3 boosts and 3 rotations. So Minkowski space has a total of 10 isometries, which is indeed a lot of isometries for 4-dimensional space-time, and is a reflection of the fact that Minkowski space is a highly symmetric space. Now, in fact, it's possible to show that any 4-dimensional geometry has at most 10 isometries. I won't prove this to you. It's not so difficult to prove. The way that you proceed is you start by adding in isometries, and if you just assume that there are 10 isometries, then you'll see that the metric takes a highly constrained form. And so what one will find is that if you look for geometries which have 10 isometries, then you find that space-time is either Minkowski space or one of two other possibilities. So it turns out that there are two other spacetimes which have 10 isometries. Here, I mean four-dimensional spacetimes, of course. So what are those two other geometries which have 10 isometries in addition to Minkowski space? Well, these geometries are also homogeneous and isotropic, and so they also have a very large isometry group. But the group of isometries, the algebra of isometries, takes a slightly different form from the form it takes in Minkowski space. So there are, these two other geometries have names. So one of them is called de Sitter space, and the other is called anti-de Sitter space. And as you proved on one of your problem sets earlier in the semester, these are maximally symmetric spaces. In the sense that the Riemann tensor is just given by a particular combination of the metric. So do you guys remember this problem on the problem set? So you verified that anti-de Sitter space and de Sitter space, maybe you only did it for de Sitter space, I don't quite remember. But you verified that anti-de Sitter space and de Sitter space have a very simple structure, namely that the Riemann tensor is given by a particular combination of the metric tensors. And indeed, one can show that anti-de Sitter space and de Sitter space have 10 isometries just like flat Minkowski space. And I won't bother writing down the metric of de Sitter space and anti-de Sitter space for you yet. I will spend some time discussing the metric of de Sitter space later. But right now, I'd like to just describe a few features of these geometries. So you should think of anti-de Sitter space and de Sitter space as spaces that are just as symmetric as flat Minkowski space, but unlike flat Minkowski space, they still have curvature. So as you showed in your problem set, de Sitter space, for example, has positive curvature, whereas anti-de Sitter space has negative curvature. And so Minkowski space, de Sitter space, and anti-de Sitter space are the three maximally symmetric spaces in four dimensions which have curvatures that are 0, positive, and negative, respectively. And so you should think of them as the space-time equivalents of flat space, the sphere, and the hyperbola. So a flat plane is a geometry that is symmetric without curvature. A sphere is a geometry which is highly symmetric, but it has positive curvature. And a hyperbola, or a hyperboloid, is a geometry which is highly symmetric and has negative curvature. And so, of course, the plane, sphere, and hyperbola are Euclidean metrics in the sense that the metric has only positive eigenvalues. And so when you're talking about Lorentzian metrics, you have slightly different geometries, but they're sort of the Lorentzian analogs of the plane, the sphere, and the hyperbola. So these are the space-time analogs of the plane, the sphere, and the hyperbola. And well, really they're the Lorentzian analogs of these four-dimensional Euclidean geometries. You're probably not so used to thinking about the four-dimensional sphere or the four-dimensional hyperbola. So for that reason, I wrote R2, S2, and H2 there. So there's a reason, however, that I'm not bothering to write down at this point the metrics of de Sitter space and anti-de Sitter space explicitly. And that is that cosmology in these three symmetric spaces is very boring. In particular, because the space-time is homogeneous, that means that physics in the far past was exactly like physics today. The state of the universe in the far past was exactly like the state of the universe today. Whereas observationally, we see that the universe has evolved over time, even at its very longest scales. And so that means that we do not live in a geometry which is exactly Minkowski space, de Sitter space, or anti-de Sitter space. And so this does not agree with observation. Indeed, if we lived in a static universe where the universe was the same at all times, the universe was eternal, and the configuration of the universe 10 billion years ago was exactly like the configuration of the universe today, there probably wouldn't be a field called cosmology. It would probably just be called astrophysics. Instead, our universe does not appear to be exactly homogeneous and isotropic. So our universe does not appear to be homogeneous and isotropic. Okay. Well, what then is the appropriate symmetry of space-time at its longest scales? Well, the point is that even though our universe does not appear to be exactly homogeneous and isotropic, it does appear to be spatially homogeneous and isotropic. In particular, if you just consider the spatial directions, rather than the space and time directions, then there does appear to be an approximate symmetry which relates every point in space to every other point in space, and any vector in space to any other vector in space. So, of course, I mean only on very large scales. Obviously, if we are considering physics at the scale of the solar system or the galaxy or even a cluster of galaxies, then the distribution of matter is very lumpy. But if you average out over long enough distance scales, then the amount of matter at any given point in space appears to be the same as the amount of matter at any other given point in space. And moreover, space looks the same in every direction. If you point your telescope in one direction and you count up the amount of matter there, it looks the same as if you point your telescope in any other direction. So that's the statement that the universe, while not being homogeneous and isotropic, is, at least at very long distances, spatially homogeneous and isotropic. So what does that mean practically? That means that at long distance scales, we can approximate the metric of our universe by a time direction and a set of three spatial directions that I will denote d sigma k squared times some function of time. Where d sigma k squared is the metric on a maximally symmetric space in 3 dimensions. So this is the spatial part of the metric. And what it describes is some 3-dimensional Euclidean geometry, which is homogeneous and isotropic in the spatial directions, and so is maximally symmetric. Yes?
When you listed the 3 maximally spaces above, was it just for Euclidean signature or any 4-dimensional?
So when I listed R3, when I listed Minkowski space, de Sitter space, and ADS space, those were the 3 symmetric spaces in Lorentzian signature. And when I listed the plane, the sphere, and the hyperbola, those are the maximally symmetric spaces in Euclidean signature. And that statement is true in any dimension. And so in a second, what I will do is I will write down for you explicitly what these 3-dimensional maximally symmetric spaces look like. Those would be the 3-dimensional versions of the plane, the sphere, and the hyperboloid. And so what is this time? What is this t coordinate? Well, this is some time coordinate. And because the metric is invariant under spatial translations and spatial rotations, the form of the d sigma squared in the metric, all of the spatial dependence in the metric is fixed. But the time dependence of the metric is not fixed, and so there's some function there called the scale factor, which I've written as a squared rather than just a, because I would like it to be positive in order for the signature of my metric to be minus 1, plus 1, plus 1, plus 1. So I chose my coefficient to be a squared rather than a, just so that my metric has exactly 1 negative eigenvalue. Now, there's a question that you could ask here, which is why don't I have some off-diagonal terms in my metric which mix the spatial directions with the time direction? And the reason is that would correspond to a preferred direction. Just as when we were considering the Schwarzschild black hole, if I had any d phi dt or d r dt or d theta dt terms, that would correspond to some preferred direction. So what do these geometries look like? So as I said before, there are 3 possible Euclidean symmetric spaces. And I have labeled them by the index k. So k here, which is the subscript that I wrote on the spatial metric, can either be minus 1, 0, or plus 1. And that labels the 3 different kinds of symmetric spaces. So let's consider the first case. So one possibility is that my spatial metric could be a flat Euclidean space. In which case the metric would just be the metric on flat Euclidean space. So that is a symmetric space in 3 dimensions. It has 6 isometries, 3 translations, and 3 rotations. Indeed, you're very used to thinking about this geometry. So this has 3 translations plus 3 rotations. And these together form a 6-dimensional group of isometries, which is called ISO3. That's just a name for that group. You don't need to remember that name. It's just a name in case you ever happen to see it anywhere. So just like the Poincare algebra of symmetries of Minkowski space was ISO 3,1. So that's one example of the possible spatial slice of our universe. The next possibility is that is what I called k equals 1. So that would be the three-dimensional sphere, S3. So what is the metric on the three-dimensional sphere? Well, there are three angular coordinates. So let's call the first coordinate d theta squared, and the second coordinate d phi squared. So there's a, well, let's write it as sine squared theta d phi squared. So if I just wrote that part of the metric here, this would be on the metric of the two-sphere, and you would be completely happy because you've stared at this metric for quite a long time already this semester. So in order to write down the metric on the three-sphere, I just have to think of this d phi squared. So for the two-sphere, that d phi squared describes a circle. And so if I want to write down the metric on the three-sphere, I just replace that d phi squared, which is a circle, by a two-sphere again. And so let's write the metric on that two-sphere as d phi squared plus sine squared phi d psi squared. So how should you think about these coordinates? Well, one way of thinking of a two-sphere is you have a theta coordinate, and for each value of theta, you have a circle, which is given by d phi. And as theta runs between, so I guess here in these coordinates, theta was the angle from the North Pole rather than the angle from the equator. So for each theta, we have a circle. And now what you do is you just imagine in your mind that instead of having a circle, what I drew as a circle here is a two-sphere. And it's the two-sphere described by the phi and the psi coordinates. So it's a little hard to visualize. But the important point that one should remember is that you can think of a three-sphere as a two-sphere, just like the line of constant latitude on the equator is a one-sphere describing the surface of the Earth, and you just replace that one sphere by a two-sphere. And just as the line of constant latitude is a circle that shrinks to zero size at theta equals 0, or theta equals pi at the north or south pole, this two-sphere on the three-sphere shrinks to zero size at the north or south pole of the three-sphere, where theta equals pi, 0, or pi. So we could just abbreviate that two-sphere by d omega squared, which I've already used as an abbreviation for the metric on the two-sphere. Are there any questions on that? Yes.
Is there any equivalent of radius or something like that on this?
We'll get to that in a second. Yes. So when I'm done writing down these metrics, I will I will use a different coordinate system, which will make the three different symmetric spaces look very similar. So here, there is a north pole at theta equals 0, and a south pole at theta equals pi. Of course, there are many other metrics on the three-sphere, just like there are many other metrics on flat three-dimensional Euclidean space. I use this metric because it makes it clear exactly how one should think about the three-sphere as the generalization of the two-sphere. And just as flat Euclidean space was a symmetric space with zero curvature, the three-sphere is a symmetric space with positive curvature. And here, the curvature which one can compute is just a number which is equal to 6. That's, of course, I could always multiply, when I write down my actual metric of space-time up here, I have some scale factor out front. So I could always absorb that factor of 6 into the scale factor. But it's conventional, it's just some convention to write my coordinates of the three-sphere in this way where I have a d theta squared without any coefficient out front. If I rescaled my metric of the three-sphere by some number, I could set the curvature equal to 1 rather than 6. Maybe that would be an intelligent thing to do. Maybe it wouldn't be an intelligent thing to do. But for historical reasons, we keep the coordinates on the three-sphere as I have written them here. Any questions on the three-sphere? The three-sphere hopefully is not that mysterious to you because it's just the natural analog of the two-sphere. Now, in your problem set that you did many weeks ago, you verified that the sphere was a symmetric space with positive curvature. I believe you did the two-dimensional sphere, which had positive curvature equal to 2 rather than 6. Is that correct? Or did I make you do the three-sphere? Maybe last year I made people do the three-sphere and they complained so much that it was just like the two-sphere that I didn't make you guys do it this year. So you should be thankful for that. It's very easy, though. I mean, you've now written in code which will do it for you in like 2 seconds. So I encourage you to test out your code by verifying that the sphere is a symmetric space with constant positive curvature. And I also encourage you to write down the metric of the 4-sphere and the 5-sphere and the 6-sphere. I've told you how to do it, right? The 6-sphere is the thing which is a theta coordinate which instead of you take the metric of the Earth, d theta squared plus sine squared theta d phi squared, and instead of the phi squared being a circle, you now replace it with a 5-sphere. What's a 5-sphere? A 5-sphere is the thing where you take the metric of the Earth and you replace the circle by a 4-sphere. And what's the 4-sphere? You can figure it out. So I encourage you to go ahead and do that. Okay. Now, let's talk about the slightly less familiar case, which was when k is equal to -1. In this case, the geometry is a three-dimensional hyperboloid H3. Oh, I should make one more comment about the three-sphere. So just as flat Minkowski space had 6 isometries, flat Euclidean space had 6 isometries, 3 rotations and 3 translations, the three-sphere also has 6 isometries. And that those 6 isometries are given by the rotation group in 4 Euclidean dimensions. Just as the isometries of the two-sphere are given by the rotation group in 3 dimensions, SO3, the isometries of the 4-sphere are given by the rotation group, a 3-sphere are given by the rotation group in 4 dimensions. And you can check this fact. And there's a name that people give for this rotation group. It's SO4. So in fact, on one of your previous problem sets, you saw explicitly that the two-sphere can be embedded in 3-dimensional Euclidean space, and that the metric of the two-sphere is inherited from the metric of 3-dimensional Euclidean space, and that allowed you to understand how the isometries of 3-dimensional Euclidean space acted on the metric of the two-sphere. And the reason why I assigned that problem to you was so that you would understand how the isometry group of the two-sphere is the same as the rotations of 3-dimensional Euclidean space. Okay, so what is the hyperboloid? Well, the hyperboloid has a metric which is nearly identical to that of the sphere, except that one of my sines becomes a sinh. Did I make you guys check that the hyperboloid was a symmetric space? If I didn't, you should do it. I think I probably took pity on you because that was a long problem set anyway. But this geometry is a maximally symmetric space with constant negative curvature, -6, rather than positive curvature, +6. And so the way that one should think about the hyperbola, or the hyperboloid, is that it is the higher dimensional version of the two-dimensional hyperboloid. And how does one think of the two-dimensional hyperboloid? Well, the two-dimensional hyperboloid is a little hard to draw, but you should think about it as the space whose metric is given by exactly that above metric, except where the two spheres are placed by a circle. And so what does this geometry look like? Well, near theta equals 0, this geometry looks like d theta squared plus sinh squared theta d phi squared. What does sinh squared look like near theta equals 0? Well, sinh squared, sinh of theta vanishes linearly in theta near theta equals 0. So near theta equals 0, it looks like d theta squared plus theta squared d phi squared. So we all recognize that metric. That is the metric of the plane. So, and the point theta equals 0 is the origin of polar coordinates on the plane. So for very small values of theta, everything looks like the geometry looks like that on a plane. And as you increase theta, we still have these circles here. But now the lengths of these circles start growing more quickly than they do in flat space. So on the flat plane, the length of a circle, a distance r from the origin, grows, the circumference of that circle grows linearly in the radius. Right? I mean, this is one of the first things you learn in elementary school. The circumference is linear in the radius. However, for the hyperboloid looks just like the plane, except the circumference grows much more quickly with the radius. For large values of this radius theta, the circumference grows exponentially in theta rather than linearly in theta. So it's a little hard to draw what that looks like. If you wanted to, what's the best way of drawing that? The best way of drawing that is to imagine starting, you could imagine your hyperbola like this, except that the lengths of these circles are growing very, very quickly. So this here would be the theta direction, and these circles would be the phi direction. And unlike in flat space, where the lengths of the circles grows linearly in the radius, here the lengths grows exponentially in the radius at large radians. So this is just some geometry which is very similar, which is sort of, at small values of the radius, at very small distance scales, it's like flat space. But if you start looking at larger distance scales, it has some curvature, which makes these circles grow in size very quickly. So that was what the two-dimensional hyperboloid was. What is the three-dimensional hyperboloid? Well, you just repeat everything I said except replacing circles by two spheres. So these surfaces would be two spheres rather than just circles. So now, if you wanted to, the subject of hyperbolic geometry and spherical geometry is, one of these very elegant subjects in 19th century classical geometry. You could take a whole class on hyperbolic geometry and spherical geometry. It's very interesting. A lot of your intuitive notions from Euclidean geometry fail to apply, and so it's a lovely subject, but it's not one which is the main topic of this class. So I will just leave you with the statement that I have now written down the metrics on the three-sphere and the hyperbola, and from those metrics you can compute whatever you like. You can study geodesics, you can compute areas, you can compute lengths, and so on and so forth. One comment I should make is that the sphere and the hyperbola are two cases where the parallel postulate of Euclidean geometry fails to hold. And so in the 19th century, it was a very fun thing for geometers to do to try and study theorems of geometry in the case where you had a geometry that was a sphere or a hyperbola. So perhaps I should end by noting that one can study the hyperbola, the hyperboloid in 3 dimensions, and show that, like the sphere and flat space, it also has 6 isometries. Now the name for the isometry group is slightly different. Here, rather than SO4 for the sphere, the isometry group of the hyperboloid is SO3, 1. In fact, you have encountered another group which is called SO3, 1. Does anyone remember what that group is? It's the Lorentz group in 4 dimensions. So just as the 3-sphere is obtained by embedding the 3-sphere in 4-dimensional Euclidean space, so that the symmetries of the 3-sphere were the rotations of 4-dimensional Euclidean space, the hyperboloid can be found by embedding the hyperboloid in 4-dimensional Minkowski space. And so the isometries of the hyperboloid are the quote-unquote rotations of 4-dimensional Minkowski space, which is what we call the Lorentz group. So I won't go through this in detail, but I did assign you an exercise near the beginning of the semester where I believe you did verify. Did you show that the hyperbola? No, you did de Sitter space. You showed that de Sitter space sits inside Minkowski space. Well, likewise, the hyperbola sits inside Minkowski space. And it's because of that, the isometry group of the hyperbola is the same as the Lorentz group. Okay. So we have these 3 different geometries. So rather than keeping track of the 3 separate cases where k is equal to -1, +1, or 0 separately, what I would like to do is to use a different coordinate system where the metric on these 3 different symmetric spaces takes the following form. So let's start by looking at flat space. So for flat space, the metric can be written in polar coordinates as dr squared times dr squared plus d omega squared. So what I would like to do is just, for the sphere and the hyperboloid, I would just like to define my radial coordinate to be the coefficient of d omega squared. So for the sphere, where the metric was d theta squared plus sine squared theta d omega squared, I would like to just define a new coordinate r, which is equal to sine theta, and then write my metric in terms of that new coordinate r. And if I let r be sine theta, then we can then write the metric in these coordinates as, so dr is minus cosine theta d theta. And so d theta squared is equal to dr squared over cosine squared theta, otherwise known as dr squared over 1 minus r squared. So the metric on the 3-sphere could be written as dr squared over 1 minus r squared plus r squared d omega squared. And likewise, on the hyperbola, I could write the metric on the hyperbola. So what was that? That was d theta squared plus sinh squared theta d omega squared. Well, now I just define r to be sinh theta, and then dr is cosh theta d theta. So d theta squared is dr squared over cosh squared theta, which is 1 plus sinh squared theta. So that's dr squared over 1 plus r squared d theta squared. And so I can look at this formula, and that formula, and this formula, d omega squared. And I can see that in all three cases, the metric on these three-dimensional geometries of constant curvature can be written as r squared d omega squared plus dr squared multiplied by a particular factor, which is 1 minus k times r squared. When k equals 0, this is flat space and polar coordinates. When k equals 1, this is the sphere written in these written in the usual coordinates, just with a rescale, with a new definition of my angular coordinate, and likewise for the hyperbola. So let me finally remind you of one more fact, which is that these spaces are symmetric spaces. So, for example, R is 0, 6, or minus 6, depending on the sign of K. So it's equal to 6K. And as you showed on your earlier problem set, for a symmetric space, the Riemann tensor is given by a particular combination of the metric. And likewise, the Ricci tensor is given by a particular combination of the metric. So the three-dimensional Ricci tensor is just a constant times the metric. Now, I just want to make my notation a little clearer here. So here, when I write down the Ricci scalar and Ricci tensor, I'm referring to the metric of the three-dimensional geometry. We'll consider the four-dimensional geometry in a minute. So I'll put a little superscript 3 there to remind ourselves that we're looking at the three-dimensional geometry. And it's conventional to put that superscript before the letter rather than after, so that you don't get it confused with any vectors that happen to be floating around. Okay, so let me just summarize. So spatial isotropy and homogeneity were enough to imply that the metric of spacetime takes the form of minus dt squared plus a squared times the metric on the spatial slice, which was dr squared over 1 minus kr squared plus r squared d omega squared, where k was either 0 or plus or minus 1. So this form of the metric is known as the FRW metric. And the geometry described by this metric is known as the FRW universe. F, R, and W standing for Friedman, Robertson, and Walker. Yes?
Is there also an L for the back to the one that proposed it in 29? No, from the Wikipedia.
There, you know, the Wikipedia page was probably written by a Frenchman. Or a Belgian.
He wouldn't have liked that.
Yeah, he wouldn't have liked that. Yeah, nobody. You know, we don't hold for Belgians in this class. Any country whose most famous resident is a fictional detective is not worth discussing. No, I mean this is always the way it works in life and in physics. It was Nikki Belgian.
Yes.
Okay. You can tell. Yeah, you can tell him I said that. You know, every you know, is it the WKB approximation? Is it the WKB whatever? You know, I mean, it all. So usually we will just call this. I will just call this an FRW universe. Maybe there's an L that goes in there. Sometimes people just call this a Friedman universe. They leave out the Robertson and the Walker. You know. Yeah, maybe there's a Lemaitre there. I'm not sure. Okay, and so there's one final comment that I would like to make, which is that although the geometry, the form of the metric looks very similar for the cases where k is equal to plus or minus 1, in fact, physically, those cases are quite different. So, in particular, when k is equal to 1, the spatial slices are spheres, and so in particular, they're compact surfaces without a boundary. You know, a sphere has finite size. And so because of that, we say that when k equals 1, the spatial slices are closed, or sometimes we just say that the universe is closed. What does that mean in particular? If the spatial slices are 1, you could, in principle, fly in a rocket ship in any direction and you would come back to yourself eventually, provided the universe didn't end first. Whereas when k is equal to minus 1, the range of that theta coordinate was infinite rather than finite. So for the sphere, the theta coordinate ran from 0 to pi. So the r coordinate ran from 0 up to 1 and then back to 0. Whereas for the hyperbolic slices, the theta coordinate ran from 0 up to infinity. And likewise, the r coordinate runs from 0 up to infinity. So the spatial slices have infinite extent, or we sometimes say that the spatial slices are open. And so this would be the case. In this case, we would say that the universe is open rather than closed. And finally, k equals 0 is the marginal case. Again, the extent of the spatial slices are infinite, but because and so this is an open universe, but because it's a sort of marginal case, sometimes we distinguish it from the k equals minus 1 case by saying that the spatial slices are flat. So that is just to distinguish it from the k equals minus 1 case, but of course they are also open. And so the universe would have spatial slices with infinite extent in that case as well. And I, of course, should remind you that the FRW metric is an accurate description for the metric of our universe only at very long scales. And so this metric describes our universe only at very long scales. Much larger than the scales on which we have any complicated structure to matter in our universe. This metric describes our universe only on distance scales long enough that the matter density of galaxies, clusters, and so forth can be averaged out. And so those are only on very long scales indeed. So at this point, we are almost done in principle with our discussion of cosmology, because now all we need to do is figure out what that function A is. But that is easier said than done. And so in order to determine A, we now need to write the equations of motion. And of course, these equations of motion will not be the vacuum Einstein's equation, because there's stuff in the universe. And so in order to write down the right equations of motion, we will need to decide what the matter content of the universe is. And this indeed is a subject that is still somewhat of an open subject. And nobody is quite sure what the matter content of the universe is. This, in fact, will not be entirely easy. Before I go ahead and do that and write down the equations of motion, maybe I should pause and see if there are any questions. Yes?
I think all we have to do is find A. What about K?
Well, and K. K is just one of three possibilities. Yes, you're right. But we need to find that as well. Okay, any questions? So we need to decide on a matter content. So, of course, the universe contains lots of stuff. It contains all stuff, in fact. Stars, galaxies, so on and so forth. But what we would like to do is take a particularly simple model which will be valid on very long distance scales. And so what we will use is what is known as the Friedman model, where the matter density is a perfect fluid. So I bet you didn't know that you were a perfect fluid, but in this Friedman approximation, you and everything else in the universe is a perfect fluid. So, and in particular, we will assume not that there is only one type of perfect fluid, but we might imagine that there's all sorts of different sorts of matter in the universe. And so, for example, there might be radiation, there might be dust, there might be a cosmological constant, so on and so forth. And so there may be many different kinds of perfect fluids which govern the dynamics of the universe. So let's first consider the case where we have a single perfect fluid. Now, we spent some time in our discussion of Einstein's equations determining the stress tensor of a perfect fluid. So let me remind you that a perfect fluid is parameterized by two numbers, or two functions, which are the pressure and the energy density of the perfect fluid. And it is also specified by a vector, which is the Frw velocity of the perfect fluid. And given a pressure and an energy density, the form of the stress tensor was completely fixed by the principle of minimal coupling. The principle of our covariantization procedure completely fixed the form of the stress tensor for a perfect fluid in terms of the energy density, the pressure density, and the Frw velocity. Now, what is the Frw velocity of the perfect fluid in the FRW model? Well, in the FRW model, we assume that the universe is spatially isotropic. So there's no special vector in the spatial directions. And so the Frw velocity can only point in the time direction. So it has to be the vector with components 1, 0, 0, 0. So what that means is that the stress tensor of a perfect fluid is really quite simple. The 0, 0 component of the stress tensor is equal to the energy density, because G00 was -1, so the pressures cancel. And the spatial components are just equal to the pressure times that spatial metric. So here I and j run from 1 up to 3 and describe the spatial indices. So given this form for the stress tensor, it's now a straightforward exercise to compute the Einstein's equations. And it's a straightforward exercise that you will do on the problem set, which is due on Monday. Tuesday, if you are not going to be here on Monday. We now just plug the metric and the stress tensor into Einstein's equations to get the equations of motion. And these equations of motion are referred to as Friedman's equations. Or occasionally as the FRW equations. So the spatial component of Einstein's equations, the Rij, or the Gij, the Ij component of the Einstein tensor being proportional to Tij, will give you an equation that is first order in the time derivatives of this scale factor A, and looks like the following. So we have an 8 pi g. That's just the factor of Newton's constant that appears in Einstein's equations. We have something that comes from the energy density, rho, because that was for T00. We have something that comes from the energy density, and we also have a curvature term that involves k. And likewise, there is a time component, which involves two time derivatives. And involves both the energy density and the pressure. And so the derivation of the Friedman equations by plugging the metric and the stress tensor into Einstein's equations is so important that I'm not going to do it for you, and instead force you to do it on your problem set. It's a completely straightforward exercise. So let's just stare at these equations for a few moments. So they tell us how A of t how the scale factor A evolves with time. There are a set of first and second order differential equations which tell us how A depends on time. And they have a dependence on K, which is the scale factor. That is K, which was this coefficient that determined whether we had open or closed spatial slices. That was 0, -1, or +1. But they also depend on P and rho. And P and rho themselves will be functions of time. So P and rho are functions of time. Intuitively, why do we expect them to depend on time? Well, the reason why we expect them to depend on time is the conservation of energy. For example, if I just have dust without any pressure, then as the universe expands, that dust will get more and more spread out because the amount energy is conserved, and so the energy density of the universe will decrease. So how do we determine how these guys depend on time? Well, we use the conservation of energy. And how is the conservation of energy written in general relativity? Well, it's written in terms of the conservation equations. So the covariant derivative of the stress tensor contracted with one of the indices of the stress tensor is equal to 0. So this, in fact, allows us to determine how the pressure and the energy evolve in time. Is there a question? You don't have conservation of energy, but you still have the relativistic version of the conservation of energy. So remember, the big deal about the stress tensor, the reason why it was that its covariant derivative is equal to 0. Now that doesn't mean that rho integrated over the geometry of space is a constant. But it does mean that there is a local conservation of energy. And so that's the principle that I use when I determine how rho and p evolve in time. So when I say conservation of energy, what I really mean is the stress tensor is conserved in the sense that its covariant derivative vanishes. And if you remember from your problem set, that was essentially a local continuity equation. And indeed, you will show in your problem set that is due on Monday that, for example, if you just look at the time component of this, so you set nu equals to 0, then you have a sum of two terms, one of which comes from the covariant derivative when mu is equal to 0, so that would be the time derivative of t0, 0, which is rho dot. And the other case, coming from the mu is equal to I case, will involve some combinations, some Christoffel symbols, and some pressures and energies. And you will show on your problem set that what you get is 0 is equal to rho dot minus 3a dot over a, p plus rho. Or, rearranging that, rho dot over p plus rho is equal to minus 3 a dot over a. So that tells us how rho evolves in time. If you know a dot, p, and rho, you can figure out rho dot. Now, at this point, the easiest way to proceed is to assume that your matter density, your matter has some, obeys some equation of state. So, for example, if we assume that our perfect fluid has an equation of state, P is equal to W rho. And indeed, if you remember from our discussion of the stress tensor, most of the fluids that we are familiar with, such as dust, a gas of radiation, mass, a cosmological constant, and so forth, all have this form where the pressure is equal to the energy density times a constant. Then, in fact, you can solve this equation for rho and determine rho in terms of A. So in particular, just plugging in that equation, we see that the left-hand side of the equation is rho dot over rho over 1 plus 1 plus W, with W being the equation of state parameter, will equal minus 3 times A dot over A. And so one can solve this, and you see that rho will grow polynomially with A. So it will be some constant times A to the minus 3, 1 plus W. So let's just check that. Rho dot over rho will be equal to A dot over A times minus 3, 1 plus W. So if you have a perfect fluid with an equation of state parameter W, then you could just go ahead and plug that in on the right-hand side of the Friedman equations. And you would get a set of differential equations for A as a function of time. So if you have, so any questions on that? So in particular, this equation tells us how matter evolves with time. So this tells us how the matter density evolves in time. And in particular, it doesn't tell us that rho integrated over our spatial slice is equal to a constant. That would be the statement that rho went like 1 over a squared. That would be just the statement that the total mass density is constant. But instead, as we know, matter can redshift or blue shift as energies can redshift or blue shift if there is a gravitational potential. And there's a sense in which the matter in the early universe was deep inside a gravitational potential well with respect to matter today. And so the reason why rho does not just fall off like 1 over a squared is you can think of it as being due to gravitational redshift. And what we have seen here is that different types of matter redshift in different ways. For example, if you have some pressureless dust, now, to first approximation, we're all just dust, right? I mean, this is in the Bible somewhere. So, if you just have some pressureless dust, by which I mean you have a perfect fluid with omega equals 0, then that means that the energy density will evolve like a to the minus 3. So as a increases, the energy density falls off like 1 over a cubed. On the other hand, if we have radiation, then this equation of state parameter was 1/3, and so the energy density falls off even more quickly, like 1 over a to the 4th power. Whereas if we have a vacuum energy, or a cosmological constant, then W was equal to minus 1, and if you look at this equation we saw up here, that means that the energy density is constant, and it doesn't fall off at all. And finally, looking at the Friedman equation up here, you can see that in this first Friedman equation, we have an energy density rho plus a contribution from curvature, and that contribution from curvature falls off like 1 over a squared. So if you treated the contribution from curvature just like it were another sort of energy density, it would fall off like 1 over a squared. So the curvature term, or the spatial slices, if you think of it as an energy density, it falls off like 1 over a squared. So, if you just had a perfect fluid with one sort, if you just had a single perfect fluid with one equation of state parameter, then it would be a straightforward manner to write down explicitly analytically what the solutions of the Friedman equations look like. But, of course, in our universe, we don't just have dust. We don't just have radiation. We don't just have curvature at a cosmological constant. We have all of these things. And so, in our universe, all of these are present. Okay, that's not quite true. Actually, observations indicate, as I'll describe next class, that the curvature term is actually 0 because k is 0. So, observationally, it is most likely the case that there's no curvature. But in principle, in the Friedman model, all of these sorts of types of matter could be present. And indeed, there could be even more kinds of matter that I haven't described here. But at the very least, we know that there is dust in our universe. There's pressureless matter in our universe. We have strong observational evidence that there's a cosmological constant or something like it, or something with vacuum energy. There's very strong evidence. I mean, obviously, there is photons and other species of particles that can move relativistically, which would give us matter with a radiation equation of state. And so, when you study the evolution of the universe, you need to take into account all of these different types of matter in Friedman's equation. So they all contribute to Friedman's equation. And so, starting next time, we will discuss the various different types of matter that are present and how the universe evolved. And I'll give you a crash course in observational cosmology and at least tell you a little bit about what the observational implications are for the mass density of the universe. But even now, you can see more or less how it is that you can more or less read off from this chart here the history of the universe. You know that the universe was very small at early times. So that means that at very early times, the dynamics of the universe was governed by radiation. When the universe was very small, photons and other species of particles were in some relativistic gas because they had lots of energy, and the universe was governed by radiation. The expansion of the universe was governed by radiation. At later times, this radiation fell off like 1/8, and instead the dynamics was governed by dust. And then the dust would disappear, and in principle we would have some curvature-dominated phase. And then at the very end, when all of this stuff is redshifted away, we're left with a cosmological constant. Now, it turns out, just to give you a little teaser for what we'll discuss next time, that this curvature term happens to be 0, and the dust and the vacuum energy terms are actually of the same order of magnitude right now. And so this is something that we'll see next class, but even just looking at this, you can read off the history of the universe. So are there any questions before we conclude? All right, see you on Thursday. Don't forget to pick up a problem set, which is due next Monday or Tuesday.